Okay, so as I promised last time, today I want to use the spherically symmetric solutions that I derived last time, okay, to solve some electrostatic problems. In particular, today, now I want to solve the problem of a charged ring. Okay. As we'll see, after solving the charged ring problem, during the solution of the charged ring problem, I'll show you that the way I do it is more general, and you can generalize it to an arbitrary spherically symmetric distribution on the xy plane. If you didn't get that, just wait and watch. Okay. For now, let's just solve this charged ring problem. Okay. So the problem is the following: you have a charged ring, which I will choose to be on the. I'll choose my coordinates such that the charged ring is on the xy plane. It's on this plane, x, y, z, and the charged ring has some radius r, and the charge of the configuration is q. Okay. And the question is, what is the potential everywhere due to this charge ring? Okay. And as I noted last time, part of this problem you might have solved as a Griffith's problem, because Griffith asked you to find the electric potential on the axis. On the axis it's easy to do, you can write down an answer. But how do you do it off of the axis? Right? That's the question. So I basically want the potential everywhere. Okay? So it's basically one duality problem. And the PDE we need to solve is just the Poisson equation equal to minus 1 by epsilon naught times the charge density. Charge density is what? I will use cylindrical coordinates rho theta phi, rho phi z. So rho is r, okay, and the charge density is just q by 2 pi r times that. Why did I put the q by 2 pi r? Because the delta function in cylindrical coordinates has this, q is just the strength of the charge. 1 by 2 pi r because the delta function has a Jacobian when we are writing it in another coordinate system. So you get 1 by 2 pi r. Or more explicitly, if you want to see it, what does this mean? I mean, the charge of the full ring is q, right? So basically, if you take this full charge density and integrate it over all of R3, which is 0 to infinity d rho, 0 to 2 pi d phi. Actually, you should put it times delta z minus 0 times the delta z, right? Maybe I should erase this. So you have q by 2 pi r delta rho minus r delta z. Okay. So if you're integrating that over all space, you need to do minus infinity to infinity dz times q over 2 pi r delta rho minus r. Remember that there should be a rho here because that's how plane polar coordinates work, right? R dr sin theta rho d rho d phi, right? Times delta of z. This delta of z kills the z integral. The phi integral just gives you 2 pi, and that 2 pi cancels this 2 pi. Delta rho minus r sets this rho to r, that r cancels this r, so this is just q. It is to ensure this fact that I just put the 2 pi r here. Right. Another way to see it is just that this is the Jacobian. Okay, so this is the problem we need to solve. Usually one forgets about this delta z and writes this as a surface charge density, right? So sigma of rho is just q by 2 pi r delta rho minus r. Okay, sigma is just the surface charge density. Don't confuse it with the conductivity. This is just the surface charge density. Okay. Great. Let's start solving this problem. Okay. Now let's say we're not on the z equals 0 plane. We're not on the xy plane. Okay. Away from the xy plane, we need to solve grad squared phi equals 0. Right? Here. Yeah. And grad squared phi equal to 0 is easy to solve because you can do variable separation. Since the charge density doesn't depend on z, actually no, let's just do variable separation. So this just becomes grad perpendicular squared, which is just del x squared plus del y squared. Okay, I just want to write it as grad perpendicular squared because transverse direction mein Laplace. Okay, if you want you can write it in rho phi coordinates. Plus del z squared acting on phi equal to 0. Now you can variable separate. Okay, so variable separation will look like phi of rho comma z. Why do I only write rho and not phi? Because this is an azimuthally symmetric problem, right? Because the charge density doesn't depend on rho, so the solution doesn't depend on rho. Okay, let me write it as phi perpendicular of rho phi z of z. If you put this ansatz in here and then divide by phi, basically you will end up getting 1 by phi perpendicular grad perpendicular squared phi perpendicular plus 1 by phi z del z squared phi z equals 0. Now you use the usual thing with variable separables, the separable method, which is to just say that this is a function of just rho, this is a function of just z. So each of these has to be a constant. Okay, so 1 by phi perpendicular. So let me just write that as grad phi perpendicular squared phi perpendicular equal to minus k perpendicular squared, where k perpendicular squared is some constant. You'll see why I am parameterizing it this way. And del z squared phi perpendicular has to be k perpendicular phi z. These two constants have to add to 0. Okay. Okay. Now why did I choose to put plus k squared here? Because remember that the charge density is located only on the xy plane. So very far away from the xy plane, if you keep going z much greater, the potential should decrease, right? It should not have an oscillatory behavior. If I put a minus k squared here and say k was real, the solutions of this will be sine and cos, and any combination of sine and cos is oscillating. Okay. I mean, you can represent it that way, but it will get far more complicated. But let's just choose positive eigenvalue here. Okay, then you can just write exponentially decaying functions. Okay. So solution of this, so immediately you got a negative eigenvalue problem, two-dimensional negative eigenvalue problem, and a one-dimensional positive eigenvalue problem. So already you start seeing that what we did last time has to kick in d equal to 1 and d equal to 2. If you are doing a sphere problem, you will get the d equal to 2. Okay, and this is why the Bessel functions in d equal to 2 are usually called the cylindrical Bessel functions, because they come up with cylindrical problems. Okay. Okay. And remember that the solution of this must only be, we only want it to be a function of rho and not phi, because we are looking for spherically symmetric solutions, and that we already know. So solution of just this is j naught of kappa perpendicular rho. Solution of this can be e to the k perpendicular rho or e to the minus k, sorry, e to the k perpendicular z or e to the minus k perpendicular z. But we want a solution such that it decays very far above and below. As z tends to infinity, it should decay. Z tend to minus infinity, it should decay. Okay. So on the z greater than 0 side, it should go as e to the minus k perpendicular z, and here it should go as e to the plus k perpendicular z. and both of which can be incorporated as e to the minus k perpendicular mod z. Okay. I am doing both at the same time, but you can actually write solution of Laplace equation above as j naught into e to the minus k perpendicular mod z, below as j naught into e to the plus k perpendicular z. And but this is a quick way of writing both the solutions together. Okay. Therefore, and this k perpendicular is not fixed. K perpendicular can be anything, because this is just some constant which has to add to 0. That constant can be anything. So you can integrate over this k perpendicular. You can take all possible k perpendiculars. Okay. So generally the solution, therefore, away from the charge density actually let me erase that and say, from the information we got by solving the Laplace equation away from the charge density, we conclude that the solution phi of rho comma z, which is just phi perpendicular into phi z, has to look like an integral over all k, okay, of j naught of k perpendicular rho e to the minus k perpendicular mod z. Okay. And you can integrate it with some arbitrary function of k perpendicular, which doesn't matter, because at every k perpendicular this is just tag along, right? Because when the Laplacian acts on this, it will come inside, because k perpendicular doesn't matter to the Laplacian will act on this, and Laplacian on this is u. So you can put some arbitrary function. Okay. Now I'll put some constants in hindsight. I'll put some constants here. Let me put a k perpendicular here. That doesn't matter, that's like a redefinition of the sigma. And I'll put a k perpendicular here. And I'll put a 2, that's again a redefinition of sigma. I'll put a 2 pi here, and I'll put an epsilon naught. You'll see in a moment why I'm putting all these numbers. Now the only thing left to do is to find the sigma, right? And how do we do that? We have already used the boundary conditions. As z tends to infinity, z tends to minus infinity, it should decay. That boundary condition gave us this particular solution. Okay. The only thing left to do is to match these two solutions above and below, okay, by this discontinuity condition, right? The fact that there is a charge density on the xy plane gives some discontinuity in the derivative of the potential, right, if you remember. So let's write that down and fix this sigma. Okay. Now why I chose to write it like this, if you want to know, is because this looks like rho d rho, okay, and this e to the minus k perpendicular mod z by 2k perpendicular is really a normalized Bessel k, or a green function in d equal to 1 in one dimension. Green functions we'll eventually see. When you see them, this will make a lot of sense to you. But at the moment, this is written without loss of generality. You need not have kept this k perpendicular and this k perpendicular. You need not have kept anything. All of this would have gone into the sigma. You could have just done it that way. But I'm putting all these constants because it looked nice. Okay. But so we did some work before getting here. We did like 15 minutes of work before getting here. But notice that this you could have written down immediately. Right? That's the power of thinking of Bessel J's this way. Okay. You could have just looked at the Laplace equation above and below. Okay. And since the problem is such that the potential has to decay in z exponentially far away. Okay. Once you do variable separation, it can in the z behavior it can either be sine or cos or exponentials. Since it has to decay, you put an exponential minus k mod z, minus k perpendicular mod z. And then the solution on the xy plane, the transverse direction solution, since this has already taken up a positive eigenvalue, there should be a negative eigenvalue problem such that the total Laplacian gives 0. So that just becomes Bessel J. So it's just Bessel J times e to the minus kz, which is this argument I ran here. but you could have done that in your head if you had some practice. Okay, and then you just have to integrate with some arbitrary function. All that is left to do is to find this function. So let's find this function. Okay, how do you find this function? By the jump condition. What is the jump condition? It's basically gotten by integrating divergence E equals rho over epsilon naught, where rho is the charge density, about, you take a small pillbox about the xy plane and integrate it. And using Gauss' law, you basically get the tangential component of E above the xy plane minus the tangential component of E below the xy plane equal to rho over the charge density, the surface charge density by epsilon naught. Once you do this, you get, remember that E vector equals minus grad phi. Okay, so you get minus del phi by del z at z equals 0 plus del phi over del z at z equal to 0 minus equal to sigma over epsilon naught, because when you are integrating this on both sides, you are integrating about a pillbox, that leaves a sigma, the z integral will get cut off. And sigma here is a function of this rho. Right? Okay, so let's feed in this ansatz that we just wrote down. Once you feed in this ansatz, what do you get? You get 0 to infinity, let's put that minus here, k perpendicular dk perpendicular over 2 pi. Bessel J will go for the ride, and then you have some sigma k which will also go for the ride, and then you have e to the minus k mod z, e to the minus k perpendicular mod z by 2k perpendicular epsilon naught. But mod z when z is greater than 0 is just z, so this is just e to the minus k perpendicular z. When you differentiate with respect to z, it brings out a minus k perpendicular. That minus gets rid of this minus, and the k perpendicular that comes out gets rid of that k perpendicular. So you just get, and then you set z equal to 0, so the exponential goes off. So you just get 1 by 2 epsilon naught. That's it. Okay, and then you do plus 0 to infinity k perpendicular dk perpendicular over 2 pi j naught of k perpendicular rho, again sigma of k perpendicular. Now when z is less than 0, e to the minus mod z is just minus z, so this becomes e to the plus k mod z, plus kz. Okay, and then when you differentiate with respect to z, k comes out, that k cancels this k, again you get a 1 by 2 epsilon naught. These two are the same, so those two add and get rid of this 2. And the epsilon naught cancels on both sides, so the epsilon naught also goes away, so you get a sigma of k. Now you see why I put 2 epsilon naught there, and why I put a k perpendicular here and a k perpendicular there, and so on and so forth. Right? All that becomes natural once you do this step. You could not have done that. I mean, you need not have done all this simplification here. You would have basically gotten the same thing. Doesn't matter. Okay. So now what is this? How do you invert this equation? How do you find capital sigma in terms of little sigma? Because that's what we want, right? Because we have a solution for phi in terms of capital sigma. Okay, but capital sigma is not what I am given. I am given the charge density on the plane, which is some sigma of rho, which I have written down there. Right? So you need to find capital sigma in terms of little sigma. But that's very easy to do once you notice that this vessel J is a spherical average. Okay, so let's write this out. 0 to infinity k perpendicular dk perpendicular over 2 pi. Bessel J0, since this is d equal to 2, is just 0 to 2 pi d phi q over 2 pi e to the I k perpendicular rho cos phi q sigma of k perpendicular equal to sigma of rho. Okay, but what is this? this is just a Fourier transform, two-dimensional Fourier transform, right? Because this thing is just d2 k perpendicular vector, right? You can think of phi q as the angle made by q perpendicular vector and k perpendicular vector, and k perpendicular as the modulus, and e to the I k perpendicular rho cos phi q is just I k perpendicular dot some r perpendicular, where r perpendicular basically means x hat or x hat plus y hat. And the direction of r perpendicular doesn't matter because you're integrating over all k perpendiculars over the whole sphere. Same arguments we did last time. Times sigma of k perpendicular equal to sigma of rho. But this is just Fourier transform. It's just Fourier transform done in both the x direction and the y direction. But this you know how to invert. This is just Fourier transform. Fourier transform ka inverse is just another Fourier transform. So sigma of k is just integral. We are missing, yeah. Now you see why I put the 2 pi there, because this becomes a 2 pi squared, and that's the usual normalization of the Fourier transform. Okay, that's how all of us write Fourier transforms, right? Remember that the convention of the Fourier transform. Let me just remind you very quickly the convention of the Fourier transform. We always write the Fourier transform like this. Say in 3 dimensions. Into e to the plus ik dot r minus I omega t, right? Phi tilde of k vector over omega. That's the Fourier transform representation. And we get exactly a 2 pi squared. We get positive ik dot r. So this inversion, in the inverse formula, remember that the inverse formula of this and the inverse formula is also easy to remember. It's just k perpendicular omega. 2 pi's always come with the momenta. 2 pi's never come with the space variables or the time variables. So it's just that. Times, here it comes with the minus k dot r plus I omega t phi of r comma omega. Okay. So you just do the inversion here. It just gives you r perpendicular sigma of rho, which is just mod r perpendicular, right? Rho is just what? Square root of x squared plus y squared, mod r, right? Times e to the minus ik dot. So we're done. Okay. Notice the important point in this derivation was this inversion, and which could be very easily done because we know the integral representation of Bessel J, because that's how we define the Bessel J, right? So just write that down. That becomes a Fourier transform. Fourier transform is invertible, so we're done. Okay. Secondly, also notice that I never put in the fact that it was a ring of charge. It could be anything as long as this is charge distribution in the xy plane, which is symmetric on the circle, which is spherically symmetric, which is what I mean by spherically symmetric and equal to 2. As long as symmetric, you can do this, right? So you've got the answer. So the solution is just some integral of Bessel J0 exponential minus k perpendicular mod z times this capital sigma, and that capital sigma is determined in terms of little sigma like this. So we're done, right? So you can do this for any kind of configuration, but let me just write down the explicit answer for the charge tree. Okay, but I guess this much makes sense, right? Actually, we can do one more step of simplification here to show an important property of these solutions. Let me just do that. So what we got there is just sigma of k perpendicular is just some Fourier transform inversion d2r perpendicular vector e to the minus ik perpendicular dot r perpendicular sigma of rho. Rho is just mod of r perpendicular. and since this depends only on rho, you can write this in plane polar coordinates. So this just becomes 0 to infinity rho d rho 0 to 2 pi d phi e to the minus ik perpendicular rho cos phi times sigma of rho. Okay. Am I missing a 2 pi? Probably not. Guessing this is correct. Anyway, so this we recognize again, okay, because this now again we define the Bessel functions, right? So this is just 0 to infinity rho d rho. You have to put a 2 pi there, then that gives a 2 pi here, and that is just Bessel J0 of k perpendicular rho of sigma. Okay, and let me write down the solution once again so that I can make this point. Solution, you just write as k perpendicular dk perpendicular over 2 pi, you get a Bessel J0 k perpendicular rho, and then the modulation is this Bessel function to k perpendicular the epsilon naught, okay, and this one. So notice what is happening. You just give me the charge distribution on the xy plane, which is the sigma of rho. What do? I Fourier transform it, which is this step. But since it's spherically symmetric, the Fourier transform is basically just doing this integral with a Bessel J0. Okay, this is really a hankel transform. This is called a hankel transform. Let me write that down. Okay, so the hankel transform is really a Fourier transform in disguise, right? It's a Fourier transform on functions which are spherically symmetric, and this can be done in arbitrary number of dimensions, by the way, because in arbitrary number of dimensions, if you add dd r e to the minus ik dot r sigma of r, this just becomes the j naught of d kappa r, right? But anyway, this is a Hankel transform. Okay, so you Hankel transform the function charge distribution you give me, okay, and then you modulate it with, so that part comes here. Once Hankel transformed, you put it here. You modulate it with this decaying exponential above and below the plane, and then you Hankel transform back. Okay. So you go to transform space, modulate, detransform, invert the transformation. Okay. So basically, like saying, if you have some problem which has translation invariance, you go to Fourier space, solve the problem there, invert. Okay. That's what we are doing here, right? In disguise, that's what we are doing. We are going to Fourier space, solving the problem, coming back. But since everything is spherically symmetric, the Fourier transform reduces to a Hankel transform. Okay. Okay. So let's solve the charge ring, because that's what I promised I will do. So let's take this and solve the charge ring, for which I have to just put. Maybe I should just do it there. Let me zoom out a bit. Good. Okay, so let's come back to charge ring. Okay. In the case of the charge ring, sigma of rho, remember, which is q over 2 pi r from the Jacobian, delta rho minus r. So sigma of k perpendicular is just 2 pi integral 0 to infinity rho d rho j naught of k perpendicular rho times q over 2 pi r delta rho minus r. Delta function will kill this integral, so that will give you this 2 pi will get rid of that 2 pi. Delta function kills this integral and makes this an r j naught of k perpendicular r. That r cancels this r. Okay, so this just gives you j naught of k perpendicular r. Simple. So then the solution is very simply integral 0 to infinity k perpendicular dk perpendicular over 2 pi j naught of k perpendicular rho e to the minus k perpendicular mod z over 2 k perpendicular epsilon naught times sigma, which is just k perpendicular. That is the full solution. For the charge ring. Okay. Now, we have not only solved the charge ring problem, we have also solved the problem for point charge. Right? Because point charge is basically taking the ring radius to 0, keeping the charge fixed. Keeping Q fixed, you take R to 0. That just gives you a point charge. But point charge, we already know the answer for the potential, it's just the Newton-Coulomb Green function. Okay? Which is basically a fancy way of saying that the answer for a point charge, maybe I should do it in the next column. For a point charge, remember that the answer for phi rho z is simply just point charge q is just q over 4 pi epsilon naught times 1 by r. Okay, but 1 by r is what? 1 by square root rho square plus x square in zero-degree coordinates. But the same answer can be derived from there, right, by putting r equal to 0. And r equal to 0 is easy to put, right? What is Bessel J0 at r equal to 0? No? Remember that when someone asks for a Bessel function, write down the spherical average. Okay? So J0 k perpendicular r, remember, is just integral 0 to 2 pi d phi q over 2 pi e to the I k perpendicular r cos phi q. If you put r equal to 0, which is j naught equal to 0, this exponent just goes away, this just becomes 1, and that's just 2 pi by 2 pi, which is 1. So j naught of 0 equal to 1. Okay? So j naught of 0 is just 1, which means the same answer, let me call this point charge, my point charge, and then I can call this phi ring, phi point charge, PC, let me call it PC, and hope it's not confusing. By the way, I think I missed a Q here, sorry, I think I missed a Q here, this Q should be here. Okay, it should be that Q. Here, so this will be Q integral 0 to infinity k perpendicular dk perpendicular over 2 pi j naught of k perpendicular rho e to the minus k perpendicular mod z over 2 k perpendicular epsilon naught. And this is just 1, which is what we just showed. And these two answers should obviously be the same. And so what we have derived is an integral representation of the Coulomb Green function or the Coulomb potential. And this integral representation is vital. Right? This integral representation is what you use to derive the method of images. If you have ever wondered how method of images works, why it works, in this Griffiths way of doing it, Griffiths does a lot of problems with method of images. Why does it work? Because of this integral representation. You can show why. I'll probably show you why in a couple of classes. So what we find by comparing these two is that 1 by square root. Let me actually put the 4 pi. Okay, because that's the most natural way to write it. 1 over 4 pi epsilon naught square root of 1 rho squared plus z squared is equal to integral 0 to infinity k perpendicular dk perpendicular over 2 pi j naught of k perpendicular rho e to the minus k perpendicular mod z over 2k perpendicular. Maybe I can get rid of the epsilon naught if you want. Yeah, 2k perpendicular. Okay. So that is an integral representation of the Coulomb. Integral representation of the Newton-Coulomb green function. I call it Newton-Coulomb because the same green function occurs in gravitational problems also when it was discovered by Newton as well. So, I guess Coulomb green function. Newton-Coulomb. aka Coulomb potential. Okay. One last thing I will say and then stop. Okay, we're already at over 30 minutes. And the last thing I want to say is if you have a small source localized very near the origin, but is not quite a point source, okay, we can obviously write down the potential because we have the answer. But can I approximate it by a point source? You would say yes, if you go very far away, you can approximate it by a point source. Okay, let me be more specific. Let me ask this question for a ring. Okay. Take a ring of radius r. Take a small ring of radius r. If you go extremely far away, the ring basically looks like a point charge to you, and you can write down the point charge answer, and you will be very much right. Okay, up to a very small error. Okay. So basically, what it tells you is that you can treat the ring as a point charge. Okay. But how do you start seeing the corrections? When do you start seeing the finiteness of the ring, finiteness of the size of the ring? Okay. So that question is what I want to answer now.